Welcome back, AP Stat. This is the third section of Chapter 14. We're going to talk about disjoint events, independent events, and how those terms relate, because they are not the same and they're often confused. Two events are disjoint if they share no outcomes. That is, they cannot happen at the same time. Another word for disjoint, or that concept of sharing no outcomes, is mutually exclusive, and I'll use those terms interchangeably. Two events are independent, on the other hand, if the occurrence of one does not affect the probability that the other occurs. The occurrence, or assumption that something has happened, doesn't affect the likelihood that something else happens. So suppose you're buying a new car, and the dealership has both gas-powered vehicles and EVs. Consider these two events. A, you select a car that runs on gasoline, and B, you select an EV. Right? Think about that. Obviously, EVs are not going to run on gas. Gasoline vehicles are not going to run on electricity. I'm not going to get technical here. Yes, there's electrical stuff in gasoline cars, and yes, you need petroleum to make a lot of the electricity we use in the EVs. I get it, fine. If you want to be a smart aleck, that's okay. But consider these two events. These events are disjoint. They can't happen at the same time. You either select an electronic-powered vehicle or you select gasoline. But are they independent? Does probability of B given A equal probability of B? Well, let's think about it. The probability of B given A is the probability that I select an EV given that I select a car that runs on gasoline. And that is going to be 0. However, the odds that I select an EV in general, that depends on the number of EVs in the lot, but assuming there are some, we have no reason to believe that the probability of selecting an electric vehicle is 0. All right? That means that these events are not independent because this probability is 0, and this probability we can more than likely assume is not 0. So many events are independent but not disjoint as well. These events just happen to be disjoint but not independent. Some events are independent but not disjoint. I'll let you think about an example of that. It is impossible for two events to be disjoint and independent simultaneously, since for disjoint events, the probability of B given A equals 0. So as long as B can happen, and that's why I have this little asterisk down here. If both events have a probability of 0, then two events can be disjoint and independent. But as long as the event B can happen, if two events are disjoint, the probability of B given A is 0. But if B can happen, the probability of B is not going to be 0. All right, so it is impossible, assuming A and B can happen, they have a probability greater than 0, it is impossible for those events to be disjoint and independent simultaneously. So now let's apply our knowledge of disjoint and independent events. A company's office of HR, reports a breakdown of employees' job type and sex as seen in the table. Right? So are being male and having a supervisor job disjoint events? And B is having a supervising job independent of whether we have a male or a female employee. In other words, is the probability of supervision given male equal to the probability of supervision, or equivalently, is the probability of supervision given female equal to the probability of having a supervision job? You can choose one or the other, and remember that independence is symmetric. So if one is independent of the other is independent of the one. Okay? So give these two problems a go, see what you get, unpause the video when you are done. Okay, let's continue. So for A, since the probability of male and supervision is not 0, Male in supervision, there are 8 people. That is clearly more than 0. Male in supervision are not disjoint. You can be a man and have a supervision job according to the HR department at this company. B is a little more interesting. The probability of supervision given male, which is what I'm going to compute, you could find the probability of supervision given female, and you will get, once we're done the problem, you'll find, not surprisingly, the same result. But probability of supervision given male is we are living in the world of men over here, and there are 60 of them, hence our denominator. And the probability that they're also in a supervision job is going to be 8 out of those 60 because there are 8 male supervisors. And that's a probability of about 13.33%. Probability of supervision in general, there are 150 total employees in this table. We have 60 men and 90 women. And there are 8 plus 12 equals 20 total supervision jobs, and this would break down to 2 out of 15, which is 13.33%. So since the odds of having a supervision job don't change based on whether we got a male or a female employee, we can say that sex and supervision are independent events. Let's take another look at a social networking survey we've seen before. Researchers reported 79% of online adults use Facebook, 24% use Twitter, and 22% apparently use both. You're familiar with this Venn diagram. You've seen it before in an earlier lesson. We have 2 questions. Are using Facebook and using Twitter mutually exclusive? And 2, are Facebooking? Oh, that's really terrible. Forgive our textbook. That's really terrible. Facebooking. Make Facebook a gerund. What are they doing? And tweeting. Okay, that's a little better. Independent. Facebooking. No one has ever said that. Okay, moving on. Are these 2 things independent? Is probability of Facebook given Twitter equal to probability of Facebook? That's one way we could do it. Or we could say probability of Twitter given Facebook equal to probability of Twitter, all right? So either of those are acceptable because, as I said before with our other HR example from the previous slide, independence is reversible. It's symmetric. If one is independent of the other is independent of the one, so you can choose how you do problem number 2. Try problem number 1 and 2 on your own if you would like. And unpause the video when you feel you have the correct answer. Okay, I'll assume we're ready to continue. Since probability of Facebook and Twitter is not equal to 0, it's actually equal to 22%, Facebook and Twitter are not mutually exclusive. They are very not mutually exclusive. You don't even need the Venn diagram to solve this. You can just look at 22% referring to this word both, and you immediately know, yeah, they're not mutually exclusive. They happen at the same time 22% of the time. So there you go. Number 2 is, as before, a bit more interesting. Probability of Facebook given Twitter, that's what we're going to find here. That's going to be 22% do both divided by 24% is a little north of 90%. But probability of Facebook in general is 79%. So it does matter whether or not we use Twitter. That does influence our probability of also using Facebook, which means Facebook and Twitter are not independent. Using one actually makes you more likely to use the other. Let's revisit a problem we've seen a little earlier. 48% of the pages in our textbook have a data display, 27% had an equation, and 7% have both a data display and an equation. So 7% have both a data display and an equation, 27% have an equation, and 48% have a data display. So we can actually complete this contingency table here for part A. Take a moment and see if you can do it by yourself. Fill in all the empty spaces with the proper percents. Okay, I'll assume we're ready to continue. If you need a little more time, pause the video again, but here we go. So 7 plus 20% equals 27%. 7 plus 41% equals 48%. And then from there, we can say 48 and 52 make 100%. 27 and 73 would make 100%. So the middle fella right here, the intersection of the nose, would have to be 32%. That is both the missing piece of 20 to get to 52 and 41 to get to 73. So that's how we complete our contingency table. Let's look at B. What is the probability that a randomly selected sample page with an equation also had a data display? All right, so we're given something here. This is the probability of data display given equation. We're assuming we're dealing with a page with an equation. So this is probability of data display given equation. Think about what that is. Try to find the probability and unpause the video when you are done. Okay, let's continue. The answer is 7 out of 27. Considering all the pages that have an equation, there are 27 that fit that category. So we have 7% that have both, 20% that just have an equation. Put it all together, you get 27%. And of that 27% we're dealing with, 7% also had a data display. So the odds would be 7 out of 27. 7 out of 100% is the probability of both, and 27 out of 100 is the probability of having an equation at all. Okay, so there you go. There's part B. Let's look at part C. Are having an equation and having a data display disjoint events? See if you can solve this on your own, and unpause the video when you are done. All right, let's continue. Well, no, since the probability of equation and display is not 0. The odds of equation and display is 7%. That is not 0. They can happen at the same time, and they do between 5 and 10% of the time. So it's not an uncommon instance either. All right, so letter D, the most interesting one. Are having an equation and having a data display independent events? Are they independent? Think about how you would confirm whether or not they're independent using the table. Try it on your own and unpause the video when you're done. Okay, I'll assume we're ready to continue. Here we go. So probability of equation given display is going to be 7 out of 48. The odds that we have a data display are 48%. And 7% of the time we have both. So 7 out of 48 would be the odds of equation given display. But the odds of an equation in general are going to be 27%. That's what we found over here, and that's also what we're given in the problem, okay? So equation and display are not independent events because we are actually, interestingly, more likely to have an equation in the general sense than have an equation given we have a data display, interestingly enough.